Yes, so thanks a lot for the invitation. I was asked to talk about hot topics in flavor physics, and I also was told that there will be dedicated talks to the anomalies now everybody is talking about, so I should try, of course, to mention it, but to circumvent it a little bit. And in principle, I was suggesting my topics into 3 categories. So hot topics, the ones, okay, which everybody is talking about nowadays, and maybe trying some aspects which might not be generally covered. When some topics which may be for some people are not so well known. And finally, some topics where, okay, some people might not have on the screen, or where some surprising results might be around the corner. Okay, you had already a proper introduction into flavor physics, into many topics. So I don't try to give a lecture, I really try to give a collection of observables, and then to discuss some of these topics a little bit more in detail, and to discuss, okay, what I think might be interesting about it. Okay, when you talk about hot topics, of course, the usual suspect, the first one we have is very, very interesting anomalies. And I think the most important thing what we need now is an independent experimental cross-check, as we would like to have for every other measurement which has such a far-reaching result. When there are some topics which are heavily discussed, like the high precision determination of CKM elements, of the CKM angle gamma, of VCB and VOB, and sometimes they have the feeling that this topic is by now considered to be a little bit boring because it's very conservative. But I would like to give you some interesting motivation for that, which might not be generally known. When there are quantities like the semi-leptonic Cp asymmetries, so this would be Cp violation in B mixing, which is in the standard model a very small number, so any sizable measurement would be an indication for some new physics. I also will mention or emphasize a little bit the experimental extraction of this Cp violating parameters in the BS system. Okay, in general, we have extremely precise measurement for the angles of the CKM elements. So we have these golden plated modes, B sub D to J psi K short, and experiment is now so precise that we have a problem in theory, and our problem is that our experimental precision is now more or less exactly at the value, which is supposed to be an uncertainty given by penguins. So for a long time we could forget about penguin pollution, and now I think penguin pollution is either we solve it, we get some more idea about it, or else it will be a kind of showstopper in order to make more use of the experimental progress. Okay, baryonic decays are extremely interesting. Cp violation was discovered in CHARM, and CHARM it's considered to be very, very small in the standard model. It was measured in so direct Cp violation was measured in D0 to pi plus pi minus versus k plus k minus, and the theory community, they all have one opinion, and that is that delta ACP is clearly governed by NP. But the question is just what is NP? And for some people, NP is clearly non-perturbative physics, while for other people, NP is clearly new physics. So that's a real tough question to answer. How big can the standard model prediction for CP violation in the D system be? And where it's important to get the control over with hadronic corrections. Okay, let me remind you a little bit about where does QCD come into the game in heavy meson decays. So I have classified meson decays. On the left, it's a leptonic decay. In the middle, it's a semi-leptonic decay. On the right, it's a non-leptonic decay. From a QCD point of view, the left one is by far the most simple one, because I have a meson decaying into leptons. For QCD, leptons are nothing. So this is a matrix element of a meson going to a vacuum. And this is typically parameterized by a decay constant. Decay constant can by now be very precisely determined with lattice QCD, so we have an amazing precision for these quantities. When I have semi-leptonic decays, we're already a little bit more complicated. I was indicating by the number of gluons which I'm drawing, but okay, don't take the gluons too serious because this is a perturbative picture, and in principle, I'm also thinking about real non-perturbative contributions, which I cannot draw by definition. Now the object is a little bit more complicated. It's one meson decaying into another meson via a current. And this is typically parameterized by a form factor. Form factors are already more complicated objects, and non-perturbative methods to determine form factors are lattice QCD and some rules. So typically we have different kinematic regions where we work best. And currently, I think most of the most precise determinations come from a combination of both methods. And finally, we have non-leptonic decays, so that's almost a disaster for theory if you look at the possibilities where you can exchange gluon. So here you have to bring in some additional assumption. In principle, you could say that this complicated matrix element of one meson decaying into two other mesons is factorizing. In one part where one meson, where the B meson decays into a D meson, and the other element, so here it would be the lower part of the diagram, I factorize it off. This would just be the pion going into the vacuum. And when the whole expression would be a form factor times a decay constant. Okay, we are studying these decays because first of all, we want to learn about parameter of the standard model, which is shown in magenta. So I have always done a big blob where the standard model, where the CKM elements are coming in. CKM elements can, for example, tell us about CP violation, and that's one of the big motivations for flavor physics. When, by comparing very precise predictions in the standard model with experiment, we could also get some bounds on your physics, and that's indicated in green. So if, for example, there would be a second Higgs doublet, when instead of the W minus, I also could exchange in all these diagrams a H minus. And by comparing experiment and standard model, I can find what's still the allowed region for such a H minus contribution. Okay, QCD I was already discussing a little bit, so I have some perturbative corrections I have to determine, and I have non-perturbative corrections here, in particular decay constant and form factors, and we have this framework of factorization. Okay, so I have drawn you only the tree-level diagrams, but this classification, leptonic, semi-leptonic, non-leptonic, you of course can also have if you have loop processes. For example, leptonic decay would be B sub S to mu plus mu minus. From a QCD point of view, it's again only a decay constant, but from an electroweak point of view, this is now a loop diagram, so you have penguin box diagram. The same is for the semi-leptonics. You could have B to K mu plus mu minus when the fundamental electroweak vertex would not be a tree-level exchange, but again a penguin or box. And you also can have similar things for non-leptonic decays. Okay, so these decays, to some extent, everything is working great. But on the other hand, we already have found some deviations, inconsistencies. And the first anomaly I would like to mention, and I call an ancient anomaly, is in the tree-level decays, semi-leptonic tree-level decays, in the determination of VOB and VCB. So VCB, we still have a kind of discrepancy between exclusive and inclusive. Somehow our understanding is progressing. Sometimes the discrepancy becomes a little bit smaller, or it's becoming larger again. When the hot topic currently are with Psl anomalies, which are rising in leptonic and semi-leptonic decays, but here in the loop decays are not the tree-level ones I was indicating here. When we have additional anomalies in semi-leptonic B to charm decays at tree-level, so with RD and RD star ratios, and I also will mention there are some discrepancies between QCD factorization predictions and with non-leptonic decays. An interesting thing for the later one is, so we have some decays like B sub S to D pi minus. So these are decays where QCD factorization should work best, and standard approach using QCD factorization and using the usual error estimates where deviate really several sigma away from the measurement. And the question is, what is it? I think many people suspect that we might underestimate some uncertainties in QCD factorization, but also here further studies really will help us to gain more insight, because when calculating with semi-leptonic decays with Psl anomalies, there's one contribution which is called a charm loop, and for this charm loop contributions, for some part, you also make assumptions similar to QCD factorization. So understanding the non-leptonic decays will also teach us something about the precision we can have in this non-local contributions to the B2SL anomalies. Okay, let's start with, as I said, some people might think this is boring because it's such an old topic, but I think there's some very interesting physics. I have taken here the PDG value for the exclusive determination of VCB. You see something like 39.5 per mil, while the inclusive determination gives 42.16. So this is a very recent determination based on a next to leading order QCD calculation, which is really quite amazing what the people in Karlsruhe did here. And whereas if you take the errors, the uncertainties serious, there's quite a difference. Now, for the inclusive, I think where some people have a monopole, so the people in Turin around Polo Gambino, there's more or less only one group. Maybe if more groups would do the estimates, there might also a smaller spread. While for the exclusive, really many groups are contributing. And here just I listed some of more recent results. So there are some results which are pointing more towards the inclusive values, but there are still many results which stay at the low value. And okay, so the question is, why should I care about it? For example, so VCB is an input into the CKM matrix. If you rely on the inclusive value, and if you then predict BS mixing, I will give you later a more precise determination. When you get the value, so that's the left-hand side, which is 18.3 with relatively large uncertainties, which matches perfectly the experimental value. So BS mixing is very precisely measured in experiment. If you look at the uncertainty, that's 0.020 inverse picoseconds. If you instead use the exclusive value, when you would predict 16.0, again, with a sizable uncertainty compared to experiment, but nevertheless, this would be a 3 sigma deviation. So if the exclusive value of VCB is the correct one, when we have a deviation in BS mixing, so we have a 3 sigma hint for new physics arising in BS mixing. And I think that's something extremely interesting, which has to be settled. Another thing, so that's a plot by Wolfgang Altmannshofer and Lewis, where also were playing what would change with the anomalies, with the B2SL mu anomalies, if I just would take different values. And actually, we were taking it around, we're saying, let's assume these branching fractions I'm measuring via standard model like, and I use them to determine VCB. And this is shown in this plot. So if you take the B2K mu decays, the red one, at the low Q squared, then you would expect a very low value of VCB of the order of 33 per mil. If you take the same at the high Q squared, that's the orange one, when you would expect the VCB, which is more or less on the exclusive side. Okay, for BS mu, also you would sit on the exclusive one. For B2XS gamma, you would be already a little bit higher. So, okay, of course, it doesn't look like a change of VCB would be a solution of the anomalies. And also you have to keep in mind for all the ratios in the anomalies with VCB dependence who cancel out. But it's just to show you how important is this value of VCB. Okay, the other, so where we don't have currently an anomaly, but the other standard model determination of CKM elements, which is assumed to be very precise, is the CKM angle gamma. Within the standard model, you can determine this CKM angle gamma with an amazing precision. So there's this famous work of Joachim and Jure, where we have shown that the standard model precision, standard model corrections are of the order of 10 to the -7. So that's really amazing. When in addition, you are using 3-level decays to extract it. So for a long time, the paradigm was there's no new physics in tree-level decays, which I think is correct if you say there's no huge new physics in tree-level decays. But at some point you might ask now, because experimental precision is increasing and theory precision is increasing. So, but for sure there's some space for new physics. The question is how much space is there? And we were playing now for years with this kind of ideas. And the first thing is very simple. So we look at the tree-level decays, for example, like B to C U bar D, so the CKM dominant B quark decay. We have an effective Hamiltonian, so we have two operators. In my notation, C2 is always the color allowed Wilson coefficient. And we just modify them. We say C2, the real C2 is the standard model C2 plus a potential new physics contribution, and also the real C1 is the standard model C1 plus a potential new physics contribution. And when you look at all observables which depend on C1, C2, where you have a reasonable experimental precision and where you have a reasonable theory precision, you make a combined fit. And then you check what's allowed. And as expected, you find for C2, which is the big Wilson coefficient, so close to 1, you find only very small deviations are possible. And for C1, you find the plot I have shown you below. So in principle, you see that with delta C1, with new physics contribution to C1 could be up to minus 0.5. Okay, so now the next question is, what does it mean? Does it have any effect if it's 0.5 or 0.5 is irrelevant? And we did a study here with Joachim Brod and Gilberto. And what we found that if there is new physics in tree-level decays, if this new physics is CP violating, then this would severely modify the extraction of gamma. And this is indicated by this line. So if you look at the upper line, I think it's a dark blue line. This is a shift in the extraction of the CKM angle gamma by the usual methods from B to decay decays of something like 6 degrees. So if the imaginary part of delta C1 could be of the order, I don't know, 0.25, 0.3, when you would get the deviation of up to 6 degrees, which is huge. So I have given you here the current precision from LHCb. This number will improve, and there are plans from LHCb, from Belle, to get down to 1 degree. So this new physics effects in tree-level decays could have a severe impact on determination of gamma. When there's another old anomaly, probably young students never have heard about it. So there was an interesting headline in 2010 in the New York Times with the title, "A New Clue to Explain Existence." And D0 was measuring a quantity which is called dimuon asymmetry. Our current understanding is that the dimuon asymmetry is a combination of ISLS, which is semi-leptonic asymmetry in the BS system, so CP violation in the BS system, a combination of the equivalent quantity in the BD system, and a combination of delta gamma D, which is the decay rate difference of neutral BD systems. So this is not settled. Currently, the discrepancy is still around 3.6 sigma. And for sure, if I look at the constraints on ASLS and ASLD, because this is also measured, so we have bounds from Bell and we have bounds from LHCb, so this alone could not solve the discrepancy. It only could be that you have also some new physics in delta gamma D, which is currently experimentally not excluded. I will show you the numbers later. We don't have a measurement of delta gamma D yet. We only have a bound, and the strongest bound is currently coming from Atlas. Okay, I was already mentioning several times mixing. I'm sure you heard it in the lectures already. Nevertheless, I would like to set my notation. So mixing is governed by these diagrams, which transfer anti-B meson into a B meson via these box diagrams. And when you calculate these box diagrams, you split up the result in two contributions. One you call M12, the other you call gamma12. M12, you call it if your internal particles, like in my left diagram, if the W minus, if they are off shell, which is always the case in the left-hand diagram, And gamma 1, 2, you call the contribution if the internal particles are on shell. So this only can happen for the right diagram and also can only happen if you have an up and a charm, because a B meson can, for example, decay into 2 D mesons. What you do, you calculate M12 gamma 12. Here I have indicated you calculate the modulus of M12, you calculate the modulus of gamma 12, and you calculate the relative phase of the two, which is denoted by phi. In the standard model, it turns out that phi is almost close to 0, so it's a very small number. Now you can relate your calculation to 3 observables. The first one is the mass difference. So originally you had the B meson and the anti-B meson defined by the quark content, which is called flavor eigenstate. When we realize we have to diagonalize the masses, we have to create linear combinations, which are given just besides the title, and you will get a light eigenstate and a heavy eigenstate. And this delta M is the mass difference between the light and between the heavy eigenstate. And if you want to calculate it, then you will see that this is just the modulus of M12. So the thing which is sensitive to virtual particles, which would in particular also be sensitive to heavy new physics particle. The decay rate difference is proportional to 2 times gamma 12, so the on-shell part. You also could have new physics where, but somehow it was for quite some time not so popular. But you could just, for example, if you exchange in the right diagram instead of the W, if you exchange a charged Higgs, when your diagram, your coupling would change, and you still could have a charm in the up as internal particles. And finally, you have this flavor-specific Cp asymmetry. So if you look at the definition, flavor-specific decay is a decay of a B meson to a final state F, where B cannot decay into F bar, and also B bar cannot decay into a F. If you now look at the definition, I'm exactly looking at that. I'm looking at B bar to F minus B to F bar. So both should not be possible. But the B bar on the left can oscillate into a B, and this B is when allowed to decay into a F. While on the right-hand side, the B can oscillate into a B bar, and this B bar can then decay into a F bar. So the only difference between the two terms is once I have mixing of B bar to B, and once I have mixing of B to B bar. And if this mixing, so if forward-backward mixing would be different, then you would get the finite value for this semi-leptonic asymmetries. And within our framework, this semi-leptonic asymmetry is given by gamma 12 over M12 times the sine of phi. So already said phi is a small number, so sine of phi is obviously also a small number. In the BS system, this is something like 1 over 250. And gamma 12 over M12 in the standard model, this is something like 5 per mil. So this is a nice null test, because standard model in the PS system gives you 2 times 10 to the minus 5. And if you measure a value of several per mil, then you can be quite sure that you have found some new physics effects. Okay, maybe I'm not talking about this in detail. You can have my slides and you can look at the references. There was quite some progress now in mixing. So mixing is dominated by the theory uncertainty. Mixing is dominated by the hadronic parameters, which are called the back parameter B and the decay constant. There's a lot of progress in lattice. Also, some rules could contribute here with a similar precision, and they give consistent results with the most recent lattice results. And these are the numbers I have shown you already. If you compare experiment and theory, then this is very nicely agreeing. Unfortunately, the uncertainties in theory are still considerably larger. When in experiment, we will be able to reduce the theory uncertainties, but surely not to a level which you already achieve an experiment now. And I have shown you here on the right-hand side also the most precise measurement of delta MS, because I will consider this decay. So it's done in a hadronic decay, B sub S to ds minus pi plus. This is also a flavor-specific decay. So the B sub S cannot decay into the antiparticle, which would be ds plus pi minus. It only can decay into ds minus pi plus. And this is also a decay. I already can mention it now. When you use QCD factorization and you predict the branching fraction and you compare it with the measured branching fraction when you are several sigmas away of each other, so which might open some new possibilities. Okay, mixing is important because, okay, there are many reasons why mixing is important, but one reason would be if the B anomalies are true, then we can look for BSM models which can explain the B anomalies, and many of these BSM models would immediately give a new contribution to BS mixing. So here I was showing you, for example, if a Z prime is the solution for the effects in BS mu, when from this BS Z prime vertex, you immediately can draw the tree-level diagram, and which is contributing to the mass difference and which is severely constraining your allowed parameter space for your new physics model. Another thing is, again, okay, you can use B-mixing for extracting CKM elements where the tops are included, because we don't have a direct handle on them, except on VTB, which we can determine via single top production. And the plot I have shown you here is the same principle I have shown you before with the anomalies. You can just take the measurement of B-mixing and assume that this measurement is consistent with the standard model value. And in the standard model, you take as only 3 parameters the CKM elements. You also assume unitarity of the 3x3 CKM matrix. And then you can use B-mixing or K-mixing for extracting the value of VCB. And if you do that, you get the value which is sitting really on top of the inclusive value, which was, if you remember when I was talking about inclusive and exclusive VCB, I said inclusive value is giving you exactly the standard model prediction is giving you exactly the experimental value for B-mixing, while exclusive is giving you a value which is much lower. So here is the same principle, just turned around. You know, use B-mixing for extracting the CKM element VCB. That's not the proof that the inclusive one is right, but you just have to keep this correlation in mind. So if you go to the exclusive one, then you prefer also to have some deviation in B-mixing, which of course could very well be the case. Okay, then other usual suspects are the semi-leptonic Cp asymmetries. So where I always like to advertise this work, which is actually going back to Anne Nelson and her former students. This was an idea of creating baryogenesis based on B mesons. So we have different models and D mesons. And what we mostly need is some new physics effects in semi-leptonic asymmetries. So that's one of the motivation, or an additional motivation why to study with semi-leptonic Cp asymmetries. You can extract them by just determining the imaginary part of gamma12 over M12. So this ratio of gamma12 over M12 is always nice because, first of all, in all the matrix elements, the QCD matrix elements which are rising, the decay constants are cancelling, and also some of the back parameters are cancelling. So these ratios are considered to be relatively precise. The real part of this ratio is delta gamma over M, and the imaginary part is ISLS. So delta M I already have told you, for gamma12 I already have told you. Gamma12 is a little bit more complicated. I don't have only one contribution, I have a real expansion, the so-called heavy quark expansion. Each term is a perturbative part times a non-perturbative part. The non-perturbative operators look similar like in delta M, but you have different Dirac structures, so you have more possibilities. And for the perturbative part, okay, you have leading terms, next to leading term, and I just have given you here a list of references who was calculating what. So just to show you that this is an advanced field, people, I don't know, I think the first calculations for the leading term started in the mid-80s, and you see where some very recent papers on were both on the perturbative side and on the non-perturbative side, and the result is given below. So if you look at delta gamma S, I have the HQE prediction on the left and the HFLAV, so the experimental average on the right. Both agree very well within uncertainties, so they overlap. The experimental precision is something like a factor 2 or 3 better, but also theory will be able to improve. My personal guess would be that the current experimental uncertainty is probably the limit on what theory will achieve in some years. For delta gamma D, we can just use the same framework in theory, so it's no problem to make a precision. But you already see that the expected value is much, much smaller than for delta gamma S, which is just CKM elements. And in experiment, we currently have only a bound. And since we don't have a measurement, since we have this bound, which still can be almost 3 times as large as the standard model expectation, this also could currently be a potential solution, okay, involving new physics, but being consistent of the Baryonic asymmetry. So here it would be really interesting to get some new result. Okay, so we have this gamma 1,2 over M12. We also can use it to predict the semi-leptonic asymmetries. I just want also to discuss the results here. ISLS in the standard model, so that's on the lower left corner with orange block, and standard model is on the right-hand side, experiment on the left-hand side. ISLS is something like 2 times 10 to the minus 5, while in experiment I have chosen the same units, or the same 10 to the minus 5 units, where the uncertainty is currently 280, so it's roughly a factor 100 times the expected standard model value. So here there's, of course, a lot of space for some new physics hanging around, and it would be very interesting to shrink this further, or maybe to identify something. In the B sub D system, expectation is roughly 5 times 10 to the minus 4, and the theory and the experimental uncertainty is already getting close, so it's 17 times 10 to the minus 4. Okay, CP violation. In general, we have 3 types of CP violation. Point 1, I was already discussing several times. Point 2, that was actually the first CP violation which was discovered. That's CP violation in the interference of mixing and decay, where you have this golden plated modes, so B sub D to J psi K short, which gives you sine to beta. The equivalent in the BS system gives you a sine to beta S. The decay would be B sub S to J psi phi. And finally, we have CP violation decay, so where you really have a direct CP violation. This would be, for example, this delta ACP, which was measured in the D system. And this listing is also a ranking according to hadronic uncertainties. So from a QCD point of view, the first asymmetry is understood best. The second one, I would say, is understood second best, because here we have a leading term which is completely free of hadronic uncertainties. And when we get some penguin contributions, so for a long time we could forget about penguins. Now experimental precision is so high that we have to care about it. And finally, we have CP violation and decay, which is extremely hard, because in order to predict that properly, I really have to understand all these QCD amplitudes. Okay, now you can look up the general time evolution of a B meson, which is just quantum mechanics. You get this complicated looking formula, but okay, in the end, it's really just quantum mechanics of a 2-state system. So my favorite reference for doing all this mixing is with old B physics at the Tevatron, but where the formulas are derived very nicely, and I never ever found a typo in this report, whether I'm always using that in this oscillation pattern. So with sine delta MT, what you get in this time evolution formula is again shown in this most recent measurement of delta MS. Okay, so let's use this formula and use the definition of CP violation in interference, so our CP violation number 2, and we assume that there is only one topology contributing. So I assume that I have only one amplitude, a 3-level amplitude, a modulus, times the e to the strong phase times the e to the weak phase. If I now insert all these things into my formula, then this QCD phase and my tree-level amplitude are completely cancelling out. So all the things I don't know, I would have to solve because they are cancelling out, and my Cp asymmetry is simply given by the weak phase difference, which is the CKM. So that's perfect. If I could do this with the decay where I don't have a second topology, when I exactly get this CKM phase, which is great. And this was also the first measurement of Cp relation in the B system in the 90s by Browder and Belle. Now, if there are two topologies, okay, I have to write my first amplitude plus a penguin amplitude. Okay, this penguin amplitude is very general. It could be a standard model penguin. It also could be a BSM amplitude. And now you do the same formalism again. When you see for the ratio of the amplitudes, you again get the CKM factor. And when you have some corrections which are proportional to R, and R is the ratio of the penguin amplitude via the tree amplitude. So naively, we expect the penguins to be smaller than the tree, but as soon as our precision is reaching values which we expect for R, when we have to work harder. And this is the so-called penguin pollution, which is naively expected to be of the order of 1 degree for sin to beta, also for sin to beta s, which is also the size where experiment is getting close now in the precision. And this is a plot which is typically shown by HFLAV. It looks at the golden plated mode B sub s to shape psi phi. And many times HFLAV, okay, I was complaining a little bit about that because we always were right as the standard model with white line. This white area was added by me by hand. And in the white line, we just take the value if you neglect penguins and we call it standard model, but that's not correct. The standard model contains this white line plus penguins. In the standard model, we know we have penguins. It's just a little bit hard to give a value. And doing this naive range of plus minus 1 degree, I get the white area. So actually, I think it would be more consistent to show a kind of white area. Of course, now people will start to fight how big is this white area, but roughly it will have this size. And you see also experiment is getting very close. If you look at the black area, so soon experiment will be as small as the standard model prediction. Okay, and finally, the worst thing are direct Cp asymmetries. So if you look at the above formula, that's a definition. Again, I insert my complicated expression I have given you for the time evolution. I do all the algebra. And when you see that the direct Cp asymmetry is directly proportional to this R. So now R is not the correction. Now R is completely giving me the whole result. So therefore direct symmetries are so hard to predict. I don't have a leading term which is free of non-perturbative uncertainties. My leading term is already the ratio of penguin over tree. Okay, I will not talk about direct asymmetries. Okay, we still have some problems around. For example, the B2K pi is not solved yet, and also with Cp asymmetry in the D system is not complete. It's not clear. So we have this nice measurement. Unfortunately, the value is just that some people still can argue, oh, maybe we have an enhancement of QCD. You need a large enhancement. So compared to naive estimates, enhancement of a factor 10, but there's also no proof that this factor 10 is not possible. So here we need to have further work. Okay, when I said there are some anomalies around which are not so well known, delta gamma D already mentioned. I will talk a little bit about BS over BD lifetime, which I think is an interesting experimental anomaly, what we have, B to D LL. So instead of BSLL, looking at the CKM suppressed contribution, which is not simply rescaling, but now because of different CKM hierarchies, it's not only the charm loop, but also the up loop, which is coming in. So we have B to S tau tau transitions, where some new physics models will say if you have B to S mu transitions, you should expect even larger B to S tau tau. So that's a relatively hot topic, and I think by now this is also discussed a lot. So here, that's something I would like to point out, tau BS over tau BD, that's the H-FLAV plot. And I have added to the H-FLAV plot the blue region, which is the standard model prediction for BS over BD lifetime. And where, if you look at the blue region, at the light blue region, the standard model and the Atlas value, you see quite a discrepancy. Also the LHC B value in the Atlas, so that's a real, that's something we have to understand, so what's going on. Of course, the combination is somehow overlapping with that, but okay, from my naive theorist's point of view, this does not look yet satisfying, and I really would like to see how this number, in particular, how the Atlas number is evolving. Do we stay at this a large value for gamma S, which is a very low value for tau PS? There was also some theory improvement, which is not included here. So it was found that in the B system, there's a large contribution from the Darwin term. And honestly, currently, we are struggling a little bit, because if you're doing some naive theory estimates for these matrix elements, which is not known, when we get a huge effect, which yeah, we are discussing now for half a year with people, and we are not really sure whether this can be or not. So we didn't publish it yet. The calculation is done. But as I said, so for this unknown, we have written rho D of PS. If we do a naive estimate, we get a huge effect. But it's very hard to do a different estimate now. So there might be some change in theory, but if this would be true, then actually our blue standard model region, it would not go to the Atlas region, it would actually go further to the left. So that's something to keep an eye open. Again, these ratios are very interesting, because in principle they also can be sensitive to new physics. As an example, I was doing again this model which is predicting a baryogenesis with B mesons. So we would have new decay channels which are more or less invisible, and these invisible decay channels would lead to some kind of lifetime difference in BS over BD or B plus over BD. And yeah, one could, by a proper study of lifetime ratios, one could get bounds on these possibilities for new physics effects. Okay, BD12, in principle, the only thing what's really to say, it's not simply an exchange of CKM elements, so it's not just VTS replaced by VTD, but it's also, as soon as you have different hierarchies now in your non-local effects, not only the charm loop, but also the up loop comes into the game, so that's quite interesting. Okay, finally, some surprise and underdogs are something which is not maybe on the radar. The first thing I was already mentioning, that there might be a problem with the BS lifetime, both in experiment, because the experimental extractions are not completely agreeing, and on the other hand also in theory, because we have this huge Darwin term where we don't know the value of the matrix element of the Darwin operator, which is with rho D, and that would be something for experiment. So my question to LHCb was always whether we have any chance of doing a kind of inclusive momentum analysis of semi-leptonic BS decays, like was done at Barber and Belle for the case of B mesons. So that's how you extract the inclusive value for VCB, if this is possible, when you could not only extract VCB, but also with parameters. And these parameters have never been extracted for the BS system. When I finally would have an experimental value for rho BS, I can insert it in my standard model prediction. I don't have to do the naive estimate I was saying before, so which was not invented by us, but which is around in the literature. And I really would see what's the standard model prediction for tau BS over tau BD. Okay, the other question I think, which currently is maybe not the most promising route, it's the question whether there will be a 5S program at Belle II. If there would be a 5S program, for sure we could do that. And I think it would be very interesting. The same principle could also be done for D mesons. And I'm always trying to convince my friends at BESS who are doing charm physics, because we just measured semi-leptonic D decays, DS plus decays, so we measured the total decay rate. Here again, if you could do With inclusive semi-leptonic decays, you could do the fit like you do for VCB, and when you would extract VCS, and also with non-perturbative matrix elements in the D system. And I will show you some results where you would need this as an input. And finally, I would like to mention a little bit with non-leptonic tree-level decays. So the question is, can there be some new physics in non-leptonic decays? Okay, maybe first, okay, I will not talk about BS again, BS I was discussing before. First, a brief statement about D lifetimes. In D lifetimes, the ratio of lifetimes is huge. So I have given you here the experimental value for D plus over D0, which is with famous factor 2.5. And the question is, can you predict such a thing? So naively in heavy quark expansion, you say the leading term is the decay of the charm quark, which is equal for all charm mesons. So naively you would expect a ratio of 1. And with 2.5 looks like a 150% correction. So at first sight, not promising. If you look a little bit closer, you will see that you have the free quark decay when you have some other contributions which are actually enhanced by a factor 16 pi squared. So 16 pi squared, that's roughly a factor 150. So maybe in the charm system with 150 enhanced contributions are actually the dominant, and it looks like that. Okay, and here a result of a recent study we did in September, or we finished in September last year. And we compare experiment and theory for the D system. In experimental numbers, always the green dots, and theory are ranges. And in principle, it looks that theory is not completely off. So of course, we have huge uncertainties, but in principle, we are lying in the ballpark of experiment. And I now show you a very complicated formula. This is, for example, the ratio of gamma of the semi-leptonic decay rate of the DS plus normalized to the semi-leptonic rate of the D0. I have inserted all numbers which are perturbative, and I just left open the non-perturbative numbers. And in the first line, you see something like mu pi of ds minus mu pi of d. So mu pi is the kinetic operator. That's a charm quark, 2 covariant derivatives, another charm quark. Mu g is the chromomagnetic operator, charm quark, gluon, charm quark, and rho d is the Darwin operator. That's charm quark, 3 covariant derivatives. And these parameters we don't know. So we can use heavy quark symmetry, we can take it from the B system, but we don't know that. And if you look, I have rewritten the formula for a second time, and you have these green blobs. And in particular, if you look at the third green blob, you see there's a big coefficient. So this ratio would be modified by 11% times the difference of the Darwin term of ds minus d. As I said, currently for that, it's like the B system, we only can do some naive estimates. We don't have a lattice determination, we don't have a summary determination, so nothing is available. If, for example, Belle III or maybe Belle II would do a momentum analysis of semi-leptonic decays, we would get numbers. And these numbers have huge coefficients. So this really would have an impact on all the results I have shown you in this table. So we try to be conservative in the shift, but maybe we even would go outside of the range, or at least we would considerably narrow our predictions. Okay, and finally, the last topic I would mention are with non-leptonic decays. So there are some decays which are, okay, there are non-leptonic decays I was introducing in the beginning, when non-leptonic decays can also have different classifications. And the simplest one are color-allowed tree-level decays. So I have drawn them here. It's a B sub S bar, ds plus pi minus. You might recognize this decay. This is the decay I always was using for the oscillation frequency. And the equivalent in the B system is B bar to D plus K minus. With a diagram, with a decays, where in the standard model you have only this contribution. So you cannot draw penguin diagram, you cannot draw an annihilation diagram, you cannot draw a color suppressed diagram. You only have one contribution, which makes them relatively easy, because these are the decays where QCD factorization should work at its best. So this complicated object is just split up in the upper line, which is the form vector, and the lower part, which would be the creation of a pion. Now, on the right-hand side, I'll show you a plot done by Nicole, comparing experiment and theory. So experiment, we just take the experimental numbers. For theory, we assume QCD factorization is working, and we do the usual estimates on which one is doing in order to get the uncertainties. And when you get huge discrepancies, so we had last week a workshop in Durham where some new Belle results were shown. I forgot, but you probably know. I think it was B to D plus pi minus, B to D star plus pi minus, and where the discrepancy is now the biggest. So you got up to 9 sigma discrepancy. Okay, so that's crazy large discrepancies. And the biggest question is what could go wrong? So if you are a scientist and don't know what's happening, you make a Twitter poll and ask your colleagues what they think about. And this I did last November, where the Belle result for BD to D plus chi minus was coming up. And naively, this was 7 sigma from QCD factorization. And I was asking my colleagues what could go wrong. So 90% assume that it's some missing or underestimated power correction in QCD factorization. Almost 10% thought it's new physics. Nobody thought it's experiments. So I suspect it was filled out only by my experimental friends. Okay, here's a list of papers who recently were working on that. And as I said already, so new physics in tree-level decays could have some serious implications. Already was mentioning this extraction of CKM gamma. This new physics in tree-level decays could also sizably enhance delta gamma T. So that's really a possibility we should discuss a little bit further. And of course, I think the biggest question, or what most people suspect, is that somehow we don't fully understand the error budget in QCD factorization, and here in Siegen some work is going on. On the other hand, you could just assume that it's correct and there is new physics in this decays, and then you can check what else is affecting that. And for example, new physics in B to C U bar D would also strongly affect the lifetime ratio of B plus over BD. I was not showing you the numbers, but here experiment and theory are agreeing very well. Here the nice thing, the problem I told you about the Darwin term is not appearing, because the Darwin of B plus is equal to the Darwin of BD zero, and it's just cancelling out. And if you're more interested, so end of May, we have a nice workshop in Siegen, which is only dedicated to the study of this hadronic decays. Okay, and my very last topic is just a strategy. How could we get more insight? So we will not be able to solve QCD exactly, which in principle we would have to do when I can give you the proper value of the branching fractions in the standard model. So I have to make this assumption of QCD factorization. Is there anything we could do else? And here I want to come back to this flavor-specific asymmetries. So we were defining with flavor-specific asymmetries. I told you it's a B to F decay, where B to F bar is not possible and B bar to F is not possible. These asymmetries are typically measured with semi-leptonic decays, and you get with experimental numbers, which I also have shown you before. Now we have this other flavor-specific decay with BS to DS plus pi minus, which was always used for the oscillations, and which also shows a discrepancy in the branching fraction if I assume QCD factorization. Okay, so let's assume that this decay, the BS DS plus pi minus, has a new physics contribution. Yeah, and I just parameterize it. I factor out the standard model contribution. When I have a 1 plus R, R is again the ratio of BSM over final state. And if this discrepancy is correct, so if QCD factorization is giving me the correct result, then I would expect that my R is of the size of 10% to 20%. Currently, I have no clue about the strong phase, so I don't know anything about my phi. and I also don't know anything about the standard model phase. Now I insert everything in my definition of my flavor-specific asymmetry. I just do the time evolution like I have shown you before, and I assume that I have two contributing decays, and I get this expression. Okay, you can look at the terms and do a good approximation. It would be the green one, which is just the Cp asymmetry in mixing times minus the direct Cp asymmetry. The direct Cp asymmetry is, to a good approximation, just 2 times R and the sign of these phases. Now, if you measure the green one with semi-leptonic decays, and you measure IFS with this non-leptonic decays, and you find a sizable discrepancies, when you have found your physics without relying on any QCD factorization or something. So therefore, I think this is a very, very promising route. So naively, if this R is equal to 0.2, when 2 times R is 40%, which is a huge number. Okay, we still could be unlucky that there is new physics, but the phases conspire in such a way that we give a 0. But okay, if we do not, then this could be extremely interesting. Okay, so that's what I wanted to say about hot topics in flavor physics, somehow avoiding a little bit the classical anomalies and try to discuss a little bit what's hanging around. So thanks a lot.
So thanks a lot, Alex, for that hot flavor talk, or garam masala as we call it. So any questions for Alex? You may type the questions on chat, or you may just ask it directly. That's fine. So while the questions come, Alex, a question on your second last slide. You had HFLAV 1970, and I didn't.
That's
that remark of yours.
That's a joke for making fun of my LHC B friends in order to put out a new analysis. So where I said the numbers are so ancient, I don't remember where they're from, probably from the 1970s. Oh. I hope to motivate them to bring out new numbers by that. I don't know if it's working.
Alex, I had a question about your NP in charm. So then whether it's non-perturbative or new physics, what things do you think we should be measuring to really help sort this out? Or if there are things that we can do, or what would be the most important inputs we could make?
Okay, I don't dare to say what is the most important input. So a very big question is how well do the theory tools, which work relatively well in the B system, work in the charm system? And one line of research, I'm not claiming it's the most important or the most best for solving this delta ACP. So one thing which I'm following is this lifetime business, because this is the total inclusive decay rate. And somehow from a theory point of view, it's a simple question. This is exactly what I have shown you. So we have this theory estimates for the charm lifetimes, for the ratios of the semi-leptonic decay rates, according to current knowledge. Our theory predictions are always agreeing, okay, maybe agreeing is too much, or always overlapping with experiment. And currently the most limiting factor, I think, is the value of these non-perturbative parameters. So that's what I wanted to motivate with asking, for example, you, Jim, measuring.
Okay, I'm regretting asking this now. Anyway, okay.
Yes. So that would be one. If, for example, we would have estimates, experimental estimates about mu pi, mu g, rho d, for the D system, for the D sub S system, when this really would help us, either in confirming that these tools are working or showing, oh, there's actually a real discrepancy showing up. So it's not one-to-one related, but it would either give us some confidence that this 1/mc expansion can also be applied in the charm sector, or it would tell us, oh, it's already failing in the simple system, so how should I ever have a chance of applying it for delta ACP where I need QCD factorization?
Okay. No. So,
but there are many. So I was quoting the review I was writing recently with Guy Wilkinson, where we also listed a lot of control channels which are more directly related. But it's okay. Unfortunately, I cannot tell you measure observer 1, 2, and then give me the result, and I tell you whether delta ACP is standard model like or not. So charm is difficult, but on the other hand, it also makes it interesting.
Sure. No, we are thinking about these types of measurements. There are some people interested, but it's going to take some time, as I've told you before, that they're quite difficult. But with the new data and stuff, it should be possible.
I really think that it would be very important and interesting.
Okay.
Namit has a question. Namit, go ahead. Okay, let me ask his question. He has it on the chat. He's asking about estimation of Darwin term contribution for lifetime.
So currently, this Darwin operator is heavy quark. So for example, let's say in the B system, it's a B bar field. When you have 3 covariant derivatives, d mu, d nu, d rho, with some contractions, and you have another field. So it's a dimension 6 operator. The quark fields dimension 3 half, 2 times dimension 3, 3 covariant derivatives dimension 6. Currently, there is no sum rule calculation, and there is no lattice calculation for such a matrix element. People just didn't consider it. The only determination is done, and it's an experimental fit. It's for the B sub D system. So where people look at semi-leptonic B meson decays, the inclusive D decays, we measure all these moments, and we make a fit on VCP, on the B quark mass, and on all the parameters. So that's the only experimental phenomenological information we have, where you have a relatively precise value for rho of BD. Now you can play with this operator a little bit. B with 3 covariant derivatives. At some point you can rewrite that in a kind of 2 derivatives. You can rewrite as a gluon field strength tensor when you have a covariant derivative acting on a gluon field strength tensor. And this you can relate by equations of motions to a quark current. So you can play around, you can do some tricks, you can then do some vacuum insertion approximation, and then you get the value. And this is what I call the naive estimate. So this was done, I think, in the 90s, many times by our Russian friends, Schiffman, Oraltsev, and also Ikaros Bigi were working on that. We were redoing that. If we do that, we get a very, very big SU3 breaking effect. But there are many assumptions going in. When you do this rewriting, you get also higher dimensional operators. We are neglecting them. So as I say, it's the only naive way which we are aware of. We redid it with new inputs, but if this would be the result when we get the huge SU3 breaking effect, which would even shift the lifetime, if you remember the plot where I have shown the Atlas result on the right, CMS and LHCP, so we would go even further to the left. And as I said, we have this result around. We now were in Munich, we were talking with all the people, Niers de Buchala, Beneke, nobody could show us any solution, but currently we don't dare to publish as long, because it would be really a big shift, and as long as we are not really sure, there might be some misunderstanding in this old estimates. We don't dare to put it out, but that's a crucial thing. And what I was asking here from the experimental side is you could determine that. You could determine that if you would do the semi-leptonic asymmetries for BS or in the D system.
Soumitra?
Hi, Alex. This is Soumitra. So one thing, since you have started about this, this non-perturbative matrix elements. So lattice probably, this Japanese group have started lattice estimate of these parameters probably for B sub D system, right? So I have one question related to this. You mentioned about B sub S system, right? Now, how bad to use the SU3 relation? Because we have already extracted the HQT parameter like mu pi square, mu g square, rho d cube, and rho ls cube. So if you use with some SU3 uncertainties in your estimates, how bad those predictions would be? I mean, for B sub S system, if you use those things.
So just the first part, Soumitra, I was not completely sure. You're talking about the inclusive decays on lattice.
Yes, inclusive decays. Yes, yes.
Which was started by Hashimoto.
Yeah. Paulo is also involved on those things.
Yes. So if I do what I was telling just now, if I use these equations of motions, when I predict the SU free breaking, and my SU free breaking is roughly FBS squared divided by FBD squared. If you insert the numbers from lattice for the decay constant of PS over BD, if you divide it, you get 50% SU free breaking, which is huge. If you now tell me, so that's also what we are thinking about, it's not a hard argument. So if you say, for example, let's assume SU free breaking is 10%, when of course the problem is softened by a factor 5. But it's a little bit ad hoc. So that's our problem. The only, I would call it still naive, but okay, better than doing nothing estimate indicates an SU free breaking of 50%, which naively to me seems too large, and I also get some severe conclusions which I would not publish now. But maybe in the end, it's what we have to do. I don't know yet.
If you have nothing, that's why I'm asking. So now, my point is that you are saying 50% breaking would be in those parameters, right? Or you are saying in the overall estimate there will be 50% error.
If I use equations of motions, when everything will be written in terms of 4-quark matrix elements, if I then use vacuum insertion approximation, the back parameters are 1, and everything is just given by the decay constant squared. And when rho BS over rho BD would just be decay constant of FBS squared divided by decay constant of FBD squared. And where I can use the lattice result, and then this is 1.45, so roughly 50%.
Okay. I have another thing. You were talking about the inclusive and exclusive determination of BCB and its impact on new physics, if I understood it correctly. Yeah. So, and what is better? You were saying inclusive determinism is worse, or the exclusive determinism is worse?
I wouldn't say better, so I wouldn't like to judge it like that. I'm just saying, if I use the inclusive value, when my standard model prediction for B mixing sits top on experiment. So if the inclusive value is correct, then there's no discrepancy in B mixing. B mixing looks standard model-like. Okay. If the exclusive value would be correct, when my standard model prediction is 3 sigma below experiment. So maybe that's the case. Maybe nature is like that. And whereas actually...
no, exclusive determinism is still not settled yet. So inclusive more or less, I mean, if the fit is correct, because not many things are missing. I mean, it's only 1 by MBQ at alpha S is missing only. So rest of the things are included only in the fit. So you can expect that the value would be more or less stable. So, but exclusive is still, there are a lot of things to understand. I mean, exclusive is a problem. I mean, recently we had in the this semi-leptonic meeting. I mean, we had a lot of discussion about this exclusive determination. So there are some issues. But okay, it's good that your inclusive is fitting. Inclusive is giving you a better result. I mean, standard model like result. So, okay.
Honestly, I also have a slight tendency for the inclusive value because I'm doing a lot of inclusive stuff. But if I could choose nature, I would prefer the exclusive one, because then I would have new physics in B mixing, which I would like even more.
Yeah. But also, I mean, point is that, I mean, exclusive, we need to, again, this form factor and these lattice calculations. And they have some sort of issues between like JLQCD have issues with milk and so familiar milk and so on. So it's not settled. That's why I'm saying. So
Yeah,
what to pick?
Therefore, I
Yeah.
was showing this list of predictions which are ranging from values to 38 and which you go up to
39 other than,
But on the other hand,
Okay, thank you.
So we are approaching the time for our next talk. So let's thank Alex again. If people can unmute themselves, they can clap, or I'll clap on everybody's behalf. So thanks a lot, Alex, and I hope you will be able
Thanks a lot. It was a pleasure.